Let's see roughly why Schmidt was so shocked and what his spectrum meant. Imagine a bright source of light which is moving rapidly away from you. The light waves that it emits are stretched out. They're moved towards longer and therefore redder wavelengths. The faster the thing is moving away from you, the more redshifted its spectral lines become. Astronomers are by now used to the conclusion that with the biggest reds, that is those which are moving fastest away from us, also the most distant galaxies. It turns out the faster a galaxy is receding from us, the swifter, the more distant it is. Now, with this information, it's possible to show roughly what Schmidt found. Schmidt's quasar spectrum is this middle spectrum. The upper and lower spectra are comparison laboratory spectra. Schmidt recognized a pattern of 3 lines due to atomic hydrogen. But these 3 lines were not in their usual place in the spectrum. Their usual place is somewhere over here. They had been redshifted by this very large distance. The amount of the redshift corresponds to a velocity of about 30,000 miles per second. And such an enormous velocity means that the quasar must be very far away. In fact, that it must be about 1 billion light years from the Earth. Now, how is it possible that an object which appears to us so bright could be so far away? A huge mass of gas or stars falling together might conceivably produce such a large amount of energy, enough to drive a quasar. But there's a problem with this idea. It's that gravity is, in a sense, too strong. There's nothing to stop the collapse of such a mass of gas or stars. It would continue to collapse. It would pass through the neutron star stage that we talked about before, and eventually its gravity would become so intense that even light would be unable to escape from the object. Therefore, the object would turn off. It would disappear. It would vanish from the universe, leaving behind only a sort of black hole of gravity, a little like the grin on the Cheshire Cat. The universe may, in fact, be riddled with such black holes. Imagine a spaceship wandering around, minding its own business, encountering such a black hole. What happens to it? Well, it must vanish. It must disappear from the universe. There are some who believe that matter which disappears down such a black hole must reemerge at some other point in space, at some other epoch in time. This may be just a sort of highbrow science fiction, or it may really be true. The quasars are such a puzzling phenomenon that they may really lead us to revise our notion of the laws of nature. It wouldn't be the first time that astronomy has taught physicists something new. But it does seem clear that simple common sense notions about the universe are just totally inadequate to account for such an extraordinary phenomenon as a quasar.
Quasars are some kind of immense explosion far away in space and time. For one point of view on them, we can turn to the radio astronomers, whose radio telescopes pick up strange radio noise. Our forefathers imagined that the heavens were filled with the music of the spheres and choirs of angels. Instead, what we hear when we convert the radio signals to sound is this hiss, like escaping steam. It brought the first news of violent upheavals in the distant universe. At Cambridge, 3 dishes, one of them movable, make up the ingenious 1-mile radio telescope. Records are obtained day by day with the movable dish in different positions along its railroad track. Combination of these records produces maps of the radio sky as detailed and precise as you'd obtain if you had one huge dish, 1 mile in diameter. There's no one around in the control room of this great telescope. It works automatically and unattended. For its patient exploration of the sources of radio noise in the universe, it's controlled by a computer. But what is it picking up out of the sky? Some radio sources are the remains of exploded stars, but others, much farther away, turn out to be exploding galaxies. Imagine a huge assembly of stars like our own Milky Way, ravaged by a central explosion far more violent than a supernova. If it happened in the Milky Way, it would wipe out all life throughout the galaxy. Such galaxies broadcast their distress by strong radio emissions across many millions of light years of space to the dishes of the telescope. The instrument reveals the shapes of the regions in and around the galaxies which are emitting strong radio waves. Those shapes tell remarkable stories of past explosions, as Anthony Hewish explains.
This is a typical radio galaxy. Just here, optical telescopes show a visible galaxy. These clouds on either side of it, which are broadcasting radio noise, are huge puffs of atomic particles wrapped in magnetic fields. We think they've been ejected by a mighty explosion in the heart of the galaxy. This pattern and the radio power are quite different from those of a normal galaxy, like this nearby spiral in Andromeda. Here, the weak radio emission matches the visible shape very closely. Sometimes it's obvious from the photograph that a galaxy is in distress. See the blobby, bright blue jet shooting out here. This galaxy is also a strong radio source, but the double cloud has not yet clearly developed. A galaxy can explode more than once. This one, mapped by radio astronomers in Australia, has a repeated double form, corresponding to one explosion long ago, with the gas clouds now stretching far across the sky, and another, much more recent, where the gas clouds are still close to the visible object. In this case, the galaxy is obscured from view in visible light, but the radio maps we've made in Cambridge suggest that it's been racked by explosions several times, like a machine gun swiveling as it fires. When we calculate the energy tied up in these radio clouds, it's amazingly large. It's as if the total energy supply of many millions of stars has been stolen and converted into high-energy atomic particles swirling in huge drifts of magnetic field. This mystery was unfolded in the early 1960s by the discovery of quasars, or quasi-stellar radio sources. These are so compact they look just like stars in both optical and radio telescopes. Yet they give off more energy than a complete galaxy. But here, a star-like visible object, optically a quasar, 3,000 million light years away, looks in our radio telescope like a typical radio galaxy. A growing number of astronomers think that quasars and radio galaxies are directly linked, roughly according to this sketch diagram here. We believe that an explosion right inside a galaxy is the visible quasar, and that this explosion throws out clouds of atomic particles, which we later observe as a radio galaxy. By studying the radio maps, we can hope to follow the evolution of this explosion, but we cannot, of course, say why galaxies explode or what causes the vast release of energy.
The nature of quasar explosions baffles the world's astronomers. It's as if many millions of stars concentrated in a volume little bigger than our solar system. Yet according to present knowledge of the forces of nature, no such concentration of matter could survive in a visible form. So quasar watching is now the first priority for the world's biggest telescopes, like the 120-inch telescope at the Lick Observatory in California. Tom Kinman is an expert on quasars, and what he's going to do tonight is measure the brightness of a quasar by comparison with nearby stars. It's hard to see anything of these little pinpoints of light unimaginably far away in space. Beside the redshift, the most striking feature of some quasars is the way they vary in brightness.
Okay, could you open the mirror, please?
The 120-inch mirror of the Lick telescope will focus the starlight to the cage where Kinman rides. This position is known as prime focus. Here, nothing stands between the big reflector and the astronomer's instruments. What staggers Kinman is that some quasars double in brightness from one night to the next. Such flashy behavior implies great violence. It also tells of extremely concentrated centers of activity in quasars. If they were big, they could not change so fast.
Try it centered now, thank you.
Thank you.
Right, I'll do yellow filter first.
Y star, C6 filter.
Right, yellow filter start.
We can see the outcome of this work in a striking way. A smaller telescope at Lick, checked with this big one, has provided our program with data for a motion picture. It shows, greatly speeded up, how the quasar called 3C345 changes in brightness in the course of a year. Every few months it doubles in brightness in a matter of days, and as quickly declines again. At Parkes in Australia, the hunt for new quasars goes on. When the telescope has pinpointed a radio source, a computer prints a map that shows its position in relation to bright stars in that part of the sky. The crosses represent the stars. Over one of the photographs from the Palomar Observatory's sky survey fits the map drawn by the computer. In this way, the source detected by the radio telescope may be related to a visible object.
We have another quasar here.
This is John Bolton.
Just a single night's observation with the 210-foot telescope can give us 100 accurate positions of radio sources. And of these, as many as 40 will be newly discovered quasars. Radio galaxies and quasars have a lot in common, but we are beginning at last to distinguish between the two classes. We observe over a wide range of wavelengths, and we find that the quasars emit more strongly at the short wavelengths. In other words, their voices are higher pitched. Even more important, we've finally begun to find out something about the size and structure of the quasars, which appear to a simple telescope as mere points of light or radio waves. In order to do this, we need two radio telescopes separated by a long distance to form an interferometer.
The interferometer is just a combination of two spaced radio telescopes. In this case, the big one is stationary and the others moving along the railroad track. Both dishes are trained on the same radio source in order to measure its size. The pens show a wavy pattern. That's because signals from the radio source in the sky arrive at the two dishes, first in step, then out of step, then in step again, as the distance between the dishes increases. When they're in step, they produce a large combined signal. Out of step, the combined signal is smaller. This happens alternately and produces the wavy pattern that the astronomers call fringes. As the separation between the dishes increases, a striking thing happens. Just watch the pen on the left. The wavy pattern starts to shrink. What's happening is that the radio source is too big to give precisely matching signals at the two dishes when they're so far apart. The bigger the source, the sooner the pattern disappears as the dishes separate.
only got about a third of the signal we started out with now. "900 feet, Ben." The fringes have completely disappeared now. You can stop the track drive. We've lost the pattern with the dishes at this separation. All we have to do now is a simple sum, which tells us the diameter of the source.
For radio sources that look very small, like many quasars, the wavy pattern will not disappear with two dishes as close as this. The first hint that quasars existed came when Jodrell Bank in England found that for some radio sources the wavy pattern persisted, even when dishes were 100 miles apart. Canadian radio astronomers at the Algonquin Observatory have pioneered a technique which allows radio telescopes thousands of miles apart to work together. By this means, even small quasars are at last yielding the secret of their true size. The trick is to make tape recordings of radio signals reviewed from a quasar at the two dishes, but to time them extremely accurately with atomic clocks. The records can then be combined as accurately as if the telescopes were really much closer together. Canadian and American astronomers have made several such links, including transatlantic ones to Sweden and Jodrell Bank in England. The first long-distance link was between Algonquin and a radio dish on the other side of Canada 2 years ago. The latest and longest link is being attempted by the Canadians right now, between the big dish at Algonquin and the big dish at Parkes, Australia. This combination makes, in effect, a radio telescope as wide as the Earth. It will give new information on the shapes and sizes of quasars, and perhaps show whether quasars are indeed exploding galaxies. Hewish at Cambridge said he thought quasars and exploding galaxies are the same kind of event at different stages. John Burton at Parkes said the quasars were higher pitched than radio galaxies, implying that they might be inherently different. But we've got other evidence from optical astronomers who can see a connection between galaxies and quasars. To tell us about that, here's Wallace Sargent at Palomar.
Galaxies are large, quasars are small, but really it isn't quite as simple as that. There are odd-looking galaxies called Seyfert galaxies. They have very bright centers. This picture of a Seyfert galaxy was taken with a long exposure. But if the exposure is significantly reduced, a star-like object sitting at the center is all that registers. It is this center that resembles a quasar, but it is 1,000 times less bright. This is the first Seyfert galaxy, which was discovered 50 years ago. In the last few years, more distant galaxies with bright centers have been discovered. This one, called 1 Zwicky 1, is the brightest galaxy known. Its center is 100,000 million times brighter than our sun. I have suggested that this object is really the missing link between galaxies and quasars. Then there are groups of galaxies in which one of them seems to be ejected with enormous energy from the rest. We call this Stephan's Quintet, and we've known about this bunch for all of 8 years. Here's a remarkable chain of compact galaxies. 4 of them are traveling together. But in 1968, I found that this one is moving away from the others at a speed of at least 15,000 miles a second. What can have happened here except some tremendous explosion? Clearly, there's something odd going on here. Either we need a new source of energy, or the familiar sources are working in ways that we haven't yet discovered. The sun and the stars generate their energy by thermonuclear reactions. But this source isn't powerful enough for the quasars. We have to think again.
On an airfield near San Francisco, astronomers prepare a telescope for flight. Here's another way to peep through the curtain of the Earth's atmosphere that cuts off most of the radiation from the universe. The telescope rides into the stratosphere in a converted businessman's jet. It's for picking up previously undetected rays coming from distant galaxies. A gold-plated telescope. In the hangar, a pioneer of infrared astronomy, Frank Lowe, of the universities of Arizona and Rice, makes ready the telescope's special detector. He has to cool it to an extremely low temperature, just 2 degrees above absolute cold. That's what he's doing here with liquid helium. Lowe wants to detect heat rays, faint infrared rays coming from far away in the universe. The warmth of his detector would swamp any such rays if he didn't make it as cold as possible. Heat is one enemy, water vapor in the air is another. Infrared rays journeying for millions of years from distant galaxies are wiped out at the last moment as they near the ground. The telescope has to go 10 miles up to get above the layer called the tropopause, where the moist air of the Earth's surface gives way to the dry air of the stratosphere. In its jacket of liquid helium, the detector fits on the telescope. The heart of the detector is a germanium crystal that is very sensitive to infrared rays.
Burton, how high do you think we'll get above the tropopause today?
Well, Frank, we're figuring on going to 50. Well, that'd be about 4,500 feet above the trope, I think, today.
The infrared galaxies that Lowe is investigating are the very same bright-centered galaxies, the Seyfert galaxies, that Wallace Sargent spoke about just now. But these galaxies generate more heat than light. Some of these heat rays do reach the ground, but are even stronger at wavelengths wholly blocked by the Earth's lower atmosphere. So, Lowe's telescope is carried 10 miles high.
Okay, we're at 50,000 feet now. We're going to go ahead and start our observation.
Roger.
Okay, Frank, this is Ron. We're level at 50,000. How's this heading look? We're heading 180 degrees now. Do you see the star?
No, not yet. We have 2 degrees more to the left.
Okay, understand. 2 degrees to the left. Stand by. Okay, rolling out. This is 2 degrees to the left now. How's that look?
Ah, there it is. I see it. I have the guide star. I'm putting it on down. Pull this heading steady. We'll start observations.
Okay, very good.
All right, here's the positive deflection. Holding that. Here's a negative deflection.
Frank Lowe testifies that heat rays from these few special galaxies equal in energy all the light from all the stars in the universe. This discovery bears out Wallace Sargent's opinion that we have to think again about the forces of nature.
Positive deflection. Okay, these data are being taken on gain 4-6. Repeat, gain.
The infrared is just one of the new windows now opening on the universe. If you had infrared eyes, here's how the sky would look. These are cool stars, or stars not quite formed. This is a bit of the sky towards the center of the Milky Way, itself a source of infrared rays. Here's how it looks by visible light. Until recently, this was the only window on the sky. Radio telescopes give quite a different picture. The ordinary stars, other than the sun, just aren't seen. Instead, violent events are picked up. Exploded stars and galaxies, pulsars, quasars. Visible light and short radio waves and some infrared are the only signals that pass unhindered through the atmosphere. Spaceflight opens up a range of new windows. As we saw earlier, with ultraviolet eyes, you'd pick out the very hot stars. And now rocket astronomers have found X-ray stars, a group of them in our same patch of sky. They're a new mystery for the astronomer. Here's the very latest window, opened by American scientists last year, using a satellite to pick up gamma rays, which are like very energetic X-rays. So far, they just show rough blocks of brightness in the Milky Way, particularly the center of our galaxy.
We should keep an eye on this part of the Milky Way, towards the center of our galaxy. Some strange things are happening there. Not only is it a source of gamma rays, but it's also an intense source of infrared radiation, as these contour maps imply. Dutch radio astronomers have found clouds of gas rushing outwards at high speed from the center of our galaxy. They imply that there was a violent event, an explosion at the center of our galaxy some 30 million years ago. It wasn't an explosion as violent as in a quasar. If it had been, we wouldn't be here today. It was just a sort of tremor.
Now we must move on to the biggest question of all, the origin and fate of the universe itself. In this connection, too, there have been astonishing discoveries just in the past few years. Are we yet smart enough to tell a true story of the universe? Men have tried to do so for centuries in various ways. According to the book of Genesis, God made the sun, the moon, and the stars to give light to the earth. He set them in the firmament of heaven. To the ancient world, the firmament of heaven meant the solid dome of the sky in which, they thought, the stars were fixed. And if a man could only look beyond the vault of heaven, he might see the cogs and flywheels that made the great dome revolve in the night. The ancient Egyptians identified the earth with the reclining god Teb. The god Shu was in the air, and reaching up to the sky, the strapping goddess Nut. In India, the Hindus pictured the earth as a sort of water lily with leaves for continents. The lotus flower was Meru, the abode of the gods. Around this, the sun and stars revolved. For Jews and Christians, too, the flat earth floated. God created Adam and Eve, and the ocean lay all around. Even as the lessons of the ancient Greeks and of the new explorers sank in, that the earth was not flat but round, they still saw the earth as the center of the universe, surrounded by the spheres carrying the heavenly bodies. And though man saw himself at the center of all things, it was a lowly place he occupied, way down in the hierarchy of archangels and six-winged seraphs. Tycho the Dane, 4 centuries ago, was the founder of modern astronomy, but he clung to the view that the earth was the center of the universe. In Tycho's cosmos, the sun still orbited Earth, but the other planets went round the sun. He rejected the system of the Polish monk Copernicus, in which all the planets were put in orbit round the sun. The muse of astronomy, for a brief period at least, gave greater weight to Tycho's universe. But the very ancient view that everything in the cosmos revolved around us had at last been discarded once and for all. The 2nd century astronomer Ptolemy, who'd crystallized that view of things, fell right out of favor. In his words, erigor dum corrigor, or, in the modern idiom, back to the drawing board. But the muse didn't favor Tycho's system very long. She heard about the Italian Galileo, his use of the telescope, and the quite novel view of the universe it provided. And in England, Isaac Newton discovered the law of gravity, the force that rules the universe. The Copernican revolution prevailed. But old habits of thoughts die hard. The sun simply replaced the earth as the center of the universe. Throughout the 18th and 19th centuries, ideas about the universe and our place in it remain very conservative. Only in the lifetime of some astronomers still alive today has it been revealed that our sun is not the center of the universe. not even at the center of our galaxy, but some way out from the center in the suburbs. Only in the 20th century have men grasped the scale of the universe, with its population of galaxies disappearing in a vast volume of space.